Good morning, student. In this lecture, we study the comparison between STATCOM and SVC fax devices. So we have individually first study the SVC as a fax device. Then after we have studied the STATCOM. So now we compare both these fax devices in terms of application in the power system. So first comparison, that is a VI characteristic of STATCOM and SVC. So as you can see in the STATCOM VI characteristics, in the capacitive region or capacitive mode, the STATCOM provide the maximum capacitive current, and this maximum capacitive current that is independent of the system voltage. It means for any low voltage condition during the large disturbance, the STATCOM provides the maximum capacitive current to maintain the voltage at the load bus near to the 1 per unit. Where it is not possible here in case of SVC, you can see that as the system bus voltage decreases, the reactive power injection by the SVC in the capacitive mode that is decreases. As you can see that as the per unit voltage decreases, the reactive power injection that is decreases. So that is the main difference between the STATCOM and SVC where we use in the power system. So in short, we can say that for the large disturbance in the power system, STATCOM provides the more voltage regulation as compared to this SVC. So with regard to the maximum transient capacitive current, it is observed that in the SVC, the capacitive current is limited by the size of the capacitor and by the magnitude of the AC voltage. So it means that you can see in this SVC characteristic, in the capacitive mode, the maximum current that is provided by the SVC that is depend upon the size of the capacitor we use. So if you may use the fixed capacitor or a thyristor switch capacitor, so the maximum capacitive current that depend upon the size of the capacitor. Where here in this STATCOM, here we use a voltage source converter to inject the reactive power to inject this capacitive current. So here the transient rating in the STATCOM that is independent of the system voltage. Clear? Where here in the SVC, the maximum amount of the capacitive power injected that depend upon the size of the capacitor as well as based on the system voltage. So as we already discussed, as the system voltage reduces or bus voltage reduces, the maximum capacitive reactive power injection that is also reduces. Clear? So that is another drawback of SVC, that with regard to the maximum transient capacitive current, it is observed that SVC, the capacitive current is limited by the size of the capacitor and by the magnitude of the AC voltage. In case of the STATCOM, the maximum capacitive current that can be injected that is limited by the maximum current capacity of the semiconductor devices. So as we know that in the STATCOM we use the IGBT or GTO based semiconductor devices. So maximum capacitive current injected by the STATCOM that depend upon the rating of the semiconductor device. If you choose the large size of the GTO IGBT, that inject the maximum current based on the rating of the semiconductor devices. But it is not depend upon the system voltage. You can see that the system voltage decreases, the maximum current capacities remain constant. Clear? Where here it is decreases with the system voltage as well as depend upon the size of the capacitor. If the size of the capacitor is small, then the maximum capacitive current provided by the SVC is also small. Now another feature of the STATCOM is that the DC link capacitor that is serve as a storage for the active power. As you know that in the STATCOM we use the voltage source converter. So input we use the DC source as a capacitor. Therefore in a certain situation, depending upon the capacitor size, it is possible to regulate the and interchange the active power with the grid also. So as we discussed in the last lecture, the theory of the STATCOM, when the DC link voltage of the STATCOM becomes lower than the required voltage, at that time we generate the output voltage of the STATCOM with the angle slightly lag behind the voltage angle of this bus voltage, so that we can transmit the active power from the system to this STATCOM, because as we know that active power transmitted from higher angle to lower angle. So we generate the STATCOM output voltage in such a way that the output voltage angle is somewhat degree lag behind the power system bus voltage, so that some active power is flow from system to the statecom, and that will charge the DC capacitor to the required level. So in the statecom, it is possible to interchange the active power also, where it is not possible in case of this SVC. In the SVC, we can interchange only the reactive power. Then statecom devices are capable of much faster dynamic reaction. It is in terms of one fourth to the 1 cycle than the SVC. It means that the statecom provides a very fast dynamic response in any large disturbance conditions as compared to the SVC. So in statecom, the speed response that is limited by the commutation frequency of the IGBT. So if the commutation frequency of the IGBT or GTO is lower, then the speed response time of the statecom also decreases. So that is the one limitation in the statecom. If the commutation frequency is low, then response time is lower. But always, as compared to the SVC, the response time is fast as compared to this SVC flex device. Now the main difference between the statecom and SVC is the way they operate. As we know that the statecom work as a controllable voltage source because we provided the converters, and this converter output voltage injected into the system to provide the compensation. While in the SVC work as a dynamically controllable reactance connected in parallel, because SVC is what basically a variable reactor or a fixed capacitor when it is connected with the system. Clear. So it is work as a controllable reactance. It may be a capacitive reactance or maybe inductive reactance. So in the statecom, when you inject the reactive power, that varies linearly with the voltage at the point of common coupling. Where in the SVC, the injection of the reactive power that is directly proportional to the square of the voltage, or it is quadratic dependence of the reactive power on the voltage at the PCC. As we already discussed in the last lecture that the reactive power injected by the statecom Q that is directly proportional to the voltage, but in case of the SVC, reactive power injected that is directly proportional to the square of the bus voltage. PCC means point of common coupling, that is nothing but a bus voltage. So at the bus voltage, so depending upon the bus voltage, the SVC and statecom injects the reactive power. So if the bus voltage reduces very slightly, then the reactive power injected by the statecom is also decreases in proportion of the bus voltage. But in case of the SVC, if a slight decrease in the voltage, that drastically reduces the injection of the reactive power because Q is directly proportional to the square of the voltage. So for a small change in the voltage, that will change the large amount of the reactive power injection in case of the SVC. So this is the main difference between the statecom and SVC. So as you can also see in the VQ characteristic also, that in the statecom we can see that as the bus voltage is reduces, the reactive power injection is also reduced in the same proportion. Clear? But here in the SVC you can see that as the bus voltage reduces, the reactive power is decreases in a square proportion, in a quadratic fashion. Clear? It means that reduces drastically in a short period of time. Clear? So this is the main difference between statecom and SVC VQ characteristic. So it means what? As compared to the statecom, for the same amount of the reactive power injection, we require the large size of the SVC, because for the small change in the voltage, that creates the large change in the reactive power injection. So for the same reactive power injection by both the statecom and SVC, we require the large size of SVC for the same reactive power injection as compared to the statecom. So that increases the ultimately cost of SVC as compared to this statecom. Now third comparison is the response time. So as we already discussed that SVCs provide the less fast response as compared to the statecom. So generally the SVC response is provided between 2.5 to 5 millisecond, but statecom provides the immediate response in 200 to 300 microseconds. So it means that statecom provide the better transient stability if sudden disturbance happen in the system as compared to the SVC. Fourth comparison point is that capability to exchange the real power. So as we already discussed that in the STATCOM it is possible to exchange the real power by changing the angle delta of the voltage source converter output voltage, but that is not possible in case of the SVC. We cannot interchange the real power with the AC system. Now fifth point is that loss versus reactive power output characteristics. So the loss contribution by the power semiconductors devices and related components in the total compensator losses is high in case of the STATCOM than the SVC. It means total losses happens in the STATCOM that is higher than the SVC. This is because presently available power semiconductor devices with internal turn-off capability that have higher conduction loss than the conventional thyristor. As we know that in the STATCOM, we use the turn-off capability semiconductor devices like GTO and IGBT. So that devices has a high conduction losses as compared to the conventional thyristors. As we know that in the SVC, we use the thyristor as a switch. So because of that, in the SVC, conduction loss is less because the conduction losses in the thyristors are less as compared to the GTO and IGBT. So that is a one drawback of the STATCOM as compared to the SVC. But as the technological development happens in the near future, then may be possible that reduce the conduction losses of this IGBT and GTO. So in the near future, we can assume that in the near future the losses of the STATCOM becomes more and more less than the SVC. Now we can see that this is a loss was the output characteristic. This is a loss was the output characteristic of the STATCOM, and this is a loss was the output characteristic of this SVC. Now, sixth point of comparison is the physical size and installation. So from the standpoint of physical installation, because the STATCOM not only controls but also internally generates the reactive power by the voltage source converter, where in the SVC the large capacitor and reactor banks are required for the reactive power injection. So as compared to the SVC, the size of the STATCOM is less because here there is no requirement of the large size of the capacitor and reactor, and with the associated switch gear and protection that we require in the thyristor controlled SVC. So overall size of the STATCOM is less as compared to the SVC. So because of that, we can reduce the overall size 30 to 40%, as well as we can also reduce the installation labor and cost of installation of STATCOM as compared to the SVC. So as the size is less, cost is less because labor cost is less. So physical size and installation is become cheap for the STATCOM as compared to the SVC. So this is a thyristor control reactor. You can see that this is the size of the thyristor control reactor we require in the SVC. Same way, this is a thyristor switch capacitor. You can see the size. So overall size of the SVC is very large. For what that you require the separate substation for installation of the SVC. Yeah. Now next point is the increase the power transfer capability of the transmission line. So here you can see that in the single line diagram of the two machine system, here is the one generator, here is the second generator. So here to transmit the maximum power over the transmission line, so for that we know that we require the flat voltage profile throughout the transmission line. But in the actual practice, what will happen? As you move away from the generator bus, then voltage at the particular bus that decreases because the voltage drop happens in the transmission line. Clear? So because of that, the power transmitted by the transmission line that is decreases, because power transmitted by the transmission line that depends upon the voltage. As we know the equation that P is equal to V square by X into sine delta. You can know this equation here in the P delta curve. P is equal to V square by X sine delta. So if V is reduces, then active power transfer also reduces. But by providing the midpoint compensation by using the SVC and STATCOM, you can increase the power transfer capability of the transmission line. So suppose assume that this is the ideal compensator and that injects the reactive power, they not inject any real power. So they maintain the midpoint line voltage Vm that is near to this sending end voltage, so that if this V2 if this V is increases, then we can increase the power transfer. Actually the equation of the P is what? V1 V2 by X sine delta. So V1 is the sending end voltage, V2 is the receiving end voltage. Clear? So here we write is a V square X by sine delta, because both the sending end voltage and the receiving end voltage are same, because we provide the compensation here by using the SVC or STATCOM and maintain the voltage at the middle point same as the sending end voltage. So it means Vs is equal to Vr is equal to Vm is equal to V. So our active power equation becomes V square by X sine delta. So by providing the compensation at the middle of the line, we can increase the power transfer capability of the line. So that can be possible by the STATCOM as well as by the SVC. So next comparison point is increased transient stability margin. I hope all of you know the what is transient stability and transient stability margin. This point, equal area criteria, transient stability margin, all this theory you already learned in the subject power system operation and control, which is taught by the Mihir sir. So I hope you understand all this concept. So I am not giving to detail about this concept. So here we first understand that how the STATCOM and SVC provide the transient stability, and in which case we get the more transient stability margin. In short, if we get the more transient stability margin, our system is more stable. Yeah. So we first see the STATCOM, then after SVC. Both are connected at the midpoint of the transmission line of the same rating of reactive power injection, and both are connected with the same system. So we first see the STATCOM, its P delta curve with equal area criteria. So here we assume that in the steady state condition, assume that the transmitted steady state power is P1 at angle delta 1. You can see that at this point power P1 and angle delta 1. And at that time the fault happens, and because of that fault the steady state power that becomes 0. As you can see that at this point delta 1 angle, the steady state power becomes 0 because of the fault condition. And during the fault, the sending end machine is accelerated. Sending end machine is this one, this is a receiving end machine. Same way in this system also, sending end machine is this, receiving end machine is this. Clear? So if the fault happens, and then during this fault, this sending machine is accelerates because the constant mechanical power is applied to this machine. Here, mechanical power is not become 0. Active power transmitted, that becomes 0. So because of the mechanical constant power provided to the machine is accelerated and that absorb the kinetic energy, and this is represented by this shaded area. You can see that here. So at this time the machine absorb the kinetic energy, and that increase the delta from delta 1 to delta C. As you can see that during this fold condition, this is the fold time, fold start at delta 1 angle, and during the fold delta 1 to delta C, the machine is accelerated because of the constant mechanical power, so that absorb the kinetic energy from the mechanical input and store it. And when the power system restore again after the fault at angle delta C, so at that time the actual power transmission that becomes increases, because now delta is increases. As we know that the active power transmission that depends upon the voltage as well as angle delta. So as the angle delta increases, the active power transmission is also increases. In steady state condition, active power transmission is P1 at angle delta 1. Clear? But after the fault, your delta is increasing from delta 1 to delta C. So it means that the actual power transmission that is increases. So what will happen? your mechanical input power provided to the generator is constant throughout the system, but reactive power transmission is increases because this angle is increases. So after this fault, after this angle delta c, this machine is deaccelerate and delta is increases still because machine has stored its kinetic energy. So after that machine is deaccelerated after the angle delta c, delta angle increases, and at that time whatever kinetic energy stored by this machine, that is released after the clearing of the fault. So whatever energy stored by the machine during this fault condition, that is released after this delta c or after the clearing time, and then after, once this energy is completely released, then again the power system come in its original position as the steady state position. You can see that after the release of the energy, again power reached to this P1 point. Clear? After the delta C, you can see that suddenly power is increased because delta is increased. Machine is deaccelerate, but angle is increased because machine has its own kinetic energy stored during the fault condition. So after the fault, all this kinetic energy is released, and once it is discharged or released, again system is regained its normal condition and reach to this steady state power level P1. So after this time, you can see that they provide certain margins for the stability. So this is the stability margin. So this area, that is called as the stability margin. So if this area is very small, that means that transient stability margin is less. It means that your system is less stable. Why? Because if the kinetic energy stored by this machine, if this kinetic energy is not released within this area and this cross this limit, then your system is collapsed, and that may create the blackout or very bad abnormal condition into the system. So to avoid this, you must provide the higher stability margin to the system. So here in the STATCOM FACS devices, they provides this stability margin, but at the same time, if you see the SVC with the same type of fault at P1 at angle delta, and that release the energy after the clearing the fault, and that takes more time or more angle to completely release the all kinetic energy from the machine. It means that the margin for the stability here, you can see that, is very less as compared to the margin which provided by the STATCOM. So it means that in the SVC they provide the less margin. It means that in the SVC your system becomes less stable as compared to the system with the STATCOM. Clear? Because that provide the more stability margin as compared to the SVC. So this is another advantage of using the STATCOM in the power system to increase the transient stability margin. So another meaning of this comparison is that for the same stability margin as the STATCOM provided here, we require the large size of the SVC as compared to the STATCOM. So this is a drawback of the SVC as compared to the STATCOM to improve the transient stability margin. So here we complete this comparison. I hope you understand all these comparison point between STATCOM and SVC. So now next point we understand, that is a power oscillation damping. So first we understand what is the oscillation and how this oscillation happens. So oscillations generally happens when any sudden disturbance or happens in the system. Sudden disturbance, like if sudden load changes, suddenly increase or decrease of the load, that may create the oscillations. So which quantity oscillation? So that is a power oscillation. So how power oscillation happens? So power oscillation happens because of minor disturbance, and because of that the machine angle that oscillates around its steady state value at the natural frequency, and because of angle oscillation, obviously your power is oscillate because power is depend upon the angle of the machine. As angle is oscillates, the power is oscillates. So the power oscillation is happens because of angle oscillation, and angle oscillation is happens because of the disturbance happen in the system. So the angle oscillation of course result in the corresponding power oscillation around a steady state power transmitted, and if you not provide the sufficient damping to this oscillation, then they create the major problem in the power system, and in some cases it may be the limiting factor of the transmissible power. So you must provide the damping, it means to reduce the oscillation by some means to avoid the any abnormal conditions. So it is necessary to vary the applied shunt compensation and thereby the midpoint voltage of the transmission line to counteract the accelerating and deaccelerating swing of the disturbance machine. So it means that how to damp out this power oscillation? So that is by providing the shunt compensation by using the Statecom or by using the SVC. So you can maintain the voltage at the middle of the transmission line to the certain level, and you can damp out the oscillation of the swing. So that is when rotating oscillating machine accelerates and angle is increases. So at that time the electrical power transmitted that must be increased to compensate the excess mechanical input power. It means that during the oscillation, during the power oscillation of the any rotating machine, if the generator accelerates, it means oscillation increases and angle increases, at that time the electrical power transmitted that must be increased to compensate the excess mechanical input power, because when your generator accelerates, when your mechanical input is higher as compared to the required value, so at that time you also increase the transmitted power so that you can compensate the excess mechanical input power. We will see in the next slide how this compensate. Same way, exactly opposite, if the generator deaccelerate, when generator deaccelerates, when the mechanical power is not sufficient to generate the required amount of the power, so at that time the generator deaccelerates, so angle is also decreases, so at that time the electrical power decrease by the compensation to balance the insufficient mechanical input power. So let's understand this concept here by the example. So this is the angle variation or angle oscillation. We can see that delta 0, that is a normal angle, normal condition, and after disturbance this angle is oscillate. You can see that this is oscillation in sine wave form, and this is a oscillation of angle. This first graph that shows the oscillation of angle with the undamped system, it means without any fixed device like Statecom or SVC, and this oscillation of the angle that is with the fixed device, it means with damping, with compensation you can decrease the oscillation of this angle. So same way you can see that the power level, as the angle oscillates, power is also oscillates, active power is also oscillates. So with undamped system, as the angle is oscillates, active power is also oscillate in the same proportion. As you can see that angle increases, the active power is also increases. As the angle decreases, active power is also decreases. And the second graph is the with damping. It means with the fixed devices, how you can reduce the oscillation of power damping. Because as they provide the compensation, oscillation of delta is also decreases. So the oscillation of active power is also reduces. So how to provide this damping? So that is by injection or absorption of the reactive power. So as you can see here in the undamped system, here the delta is increases. It means this is the acceleration of the machine. So at that time you increase the active power. So how to increase the active power? So for that you require the reactive power compensation. So by reactive power compensation you can maintain the system bus voltage in such a way that you can increase the active power transmission. So here you can see that during the acceleration of oscillation, the compensating device, it may be a Statecom or SVC, that inject the reactive power into the system and that increase the active power transmission. Clear? During the acceleration point. At the same time, you can see that during the deceleration, it means when delta is decreasing, during the deceleration, we require to absorb the excess active power from the system. So at that time, you can see that active power reduces by the absorption of the or by the injection of the lagging reactive power. So you can see that in this case, deceleration case, the compensating device reduces the reactive power so that decrease the oscillations or decrease the active power transmission. So based on the active power injection and absorption, they provide the damping into the power system. You can see that initial period of time, damping is not wipe out suddenly, but in the after some time in steady state condition, you can see that here after 2 or 3 cycle, that damp out all the oscillations. And you can see that once the damp out all the oscillation, it means when the system regain its normal angle delta, here after 3 cycle you can see that here your machine reaches the normal angle delta, it means oscillation is wiped out. So at that time the reactive power also regains its normal power P0, and at the same time the reactive power injection or absorption by this compensation also becomes 0. So based on this injection and absorption of the reactive power, you can wipe out this oscillation into the system and you can reduce the power oscillation so that it cannot create any abnormal conditions. So this is all about the power oscillation damping. So this power oscillation damping is provided by the STATCOM as well as the SVC. So let's recall again the comparison between SVC and STATCOM. So as we know, as STATCOM is faster response as compared to SVC. So faster, SVC is slower than STATCOM. Cost is high. Why cost is high in the case of this STATCOM? Because we require the voltage source converters. In that we require the number of multi-level converters. If we increase the number of levels, as we see in the MATLAB simulation, we require the number of multi-level converters in the 48 pulse VSI. So because of that, the cost of the STATCOM is higher as compared to the SVC, but size of the STATCOM is less as compared to the SVC. Losses are higher, as we already discussed why losses are less. Better characteristic in the STATCOM, VI characteristic is better as well as VQ characteristic as compared to the SVC. That provide the constant current characteristics in the capacitive mode, but here in the SVC the capacitive current limit that is reduces linearly with the system voltage. That interface with the real power sources like battery, fuel cell, but here there is no any real power interference with the SVC. Smaller in size, larger in size, that act as a controllable voltage source and that act as a dynamically controlled reactance. And one point missing here, that is STATCOM provides a better transient stability margin as compared to this SVC. So this is all about the comparison between STATCOM and SVC. I hope you understand this lecture. If you have any query or doubt, you can discuss with me during the doubt solving session or you can mail me. Next lecture we discuss the next FACS devices that is called as thyristor controlled series capacitor. Thank you.